Four inner worlds drift in the darkness, held in a quiet orbit around the same star. They look simple from afar, just four pale circles painted on a black canvas. But if you place them side by side, something unsettling appears. Each one is the survivor of an ancient experiment, and none of the outcomes match. Mercury is metal stripped bare. Venus is a furnace sealed behind pale clouds. Earth is a fragile oasis wrapped in blue. Mars is a frozen echo of rivers that vanished long ago. Nothing about their shared origin explains how violently their fates diverged. Imagine them suspended before you, turning slowly in silence. Mercury is small and bright, polished by centuries of sunlight that fall on its cratered skin without mercy. Venus glows through a cloud veil so thick that not even orbiters can see the surface directly. Earth rotates with a soft shimmer of oceans reflecting light back into space. Mars turns like a fading ember, its red soil cold and ancient. Four worlds, each no more than a few minutes apart in cosmic distance, yet separated by gulfs of destiny. The paradox is immediate and sharp. Why does the closest planet to the sun swing between deep space, cold, and blazing heat? Why does the world beyond it trap so much warmth that its entire surface bakes hotter than fresh metal? How does Earth manage to stabilize oceans and weather while receiving almost the same sunlight as Venus? How did Mars lose its air and water even though its valleys still show the fingerprints of ancient floods? If distance were the only rule, these worlds would form a smooth gradient. Instead, they form a broken sequence. Fire, metal, life, and dust. Picture Mercury first. The sun fills a large part of its sky, so large that shadows twist and bend with the slow turning of the world. A single day there lasts 2 full years. At one point, the sun seems to stop, then drift backward, then resume forward again. The surface is a field of stone shattered by billions of impacts, caverns of shadow never warm, while the day side glows with heat fierce enough to warp metal. There is no air to breathe, no sound to hear. It feels like the world has been stripped to its bones. If you stood there, you would feel the emptiness pressing in from every direction. Now shift your view to Venus. From a distance, it looks gentle, almost serene, a pale lantern reflecting sunlight with elegance. But as you descend through its cloud cover, the illusion dissolves. The air thickens until it feels like an ocean made of invisible weight. Every step would feel like wading through warm, heavy fluid. The ground is hot enough to melt lead. The pressure is strong enough to crush hardened steel. Winds higher in the atmosphere race around the planet at incredible speeds, carving patterns in the sulfur clouds. Everything about Venus is intense, concentrated, and unwilling to let heat escape. It is a world where warmth becomes a trap and the sky becomes a wall. Then comes Earth, an anomaly among its siblings. Its oceans store sunlight. Its atmosphere lets heat in and lets it out in a delicate rhythm. Its magnetic field bends the solar wind so it brushes past instead of tearing the air away. Seasons rise and fall with a tilt that shapes every coastline and forest. Here, water can be liquid, solid, or vapor. Light scatters into blues and greens. Life clings to every surface, from volcanic vents to frozen deserts. The balance looks effortless when viewed from orbit. Up close, it is the product of 1,000 narrow conditions that could easily have gone another way. The thin line between habitability and sterility becomes clear only when you compare Earth to its neighbors. Finally, look at Mars. Its deserts stretch wider than continents. Its sky is thin enough that a breeze feels like a whisper. In winter, slabs of carbon dioxide freeze on the poles. In spring, they sublimate into winds that lift dust across entire basins. Yet the surface holds ancient memories. Dry riverbeds snake across valleys. Deltas remain sculpted in perfect detail. There are minerals that only form in the presence of water. Mars looks like a world that once held promise and then slowly let it slip away. The blue it once reflected is gone, What remains is a library of clues carved into stone and ice. These four worlds should not be so different. The early solar system shaped them with the same heat, the same gravity, the same storms of rock and ice. They were born from the same rotating cloud. They moved through the same furnace of collisions. Yet their paths split in ways that defy simple explanation. A slightly heavier core here, a slightly thicker atmosphere there, a rotation that locks into a strange rhythm, a magnetic field that forms in one world, but not in another. In the first few million years after the sun ignited, these small differences were amplified by time until they sculpted four entirely separate destinies. To understand this divergence, imagine the sun not as a steady source of light, but as an engine that shapes everything within reach. It warms, burns, pushes, and strips. It sculpts atmospheres. It torques rotation. It charges particles that slam into magnetospheres and carve invisible rivers of energy. Each planet responds differently to this pressure. Mercury shrugs off air. Venus holds it like a sealed chamber. Earth balances it with oceans and clouds. Mars loses it slowly to the solar wind. The sun is not simply a lamp in the sky. It is a sculptor with immeasurable patience. If we stand far enough back, these four worlds resemble a sequence of experiments. What happens when a world is too small? What happens when a world traps its heat? What happens when a world receives just enough sunlight for oceans? What happens when a world loses its magnetic shield? Each answer shapes the landscape, the sky, and the future of the planet. Each answer suggests a branch in a cosmic decision tree, one that repeats across the galaxy wherever young stars form their planets. Now imagine an explorer drifting above these four worlds, watching them circle their star. The contrast is impossible to ignore. Mercury races round and round, never quite escaping the furnace. Venus spins slowly backward, its surface hidden from view. Earth rotates steadily, wrapped in swirling white storms. Mars turns quietly, its thin air glowing faintly with dust. It is like watching four clocks tick at different speeds. Each one measures time in its own strange way. Each one records the story of heat, gravity, and memory. But here is the deeper question. If our own solar system produced such a wide spread of outcomes with so little variation in distance, what happens in systems far more chaotic or more ordered than ours? Could life appear on worlds with thicker air than Earth? Or thinner? Could oceans form beneath clouds as bright as Venus? Could rivers flow on planets with orbits more eccentric than Mars? The four inner planets hint that the possible outcomes for worlds are more varied than we once believed. We stand on Earth and look outward, trying to understand what makes our world special. But the answer may not lie in Earth alone. It may lie in the contrast. The metal heart of Mercury, the pressurized ovens of Venus, the ancient riverbeds of Mars. Together they form a scale of possibilities, a spectrum of what can happen when a star tries to build stable surfaces in a hostile universe. They remind us that even small differences in formation echo across billions of years. As we continue to study these worlds, we read their surfaces like old manuscripts. Craters record violence. Volcanoes record heat. Atmospheres record loss and renewal. Magnetic fields record motions deep below the crust. Every world is a chapter in the story of how planets rise, change, and fade. And every clue we gather from them sharpens our understanding of what a habitable world really requires. Here is the open loop that pulls us forward. If four planets born side by side diverged so completely, then perhaps the universe is filled with variations stranger than we imagine. Perhaps the next Earth-like world will not resemble Earth at all. Perhaps the corridor for life is wide, or narrow, or shifting. To understand our own future, we must walk through the archives of Mercury, Venus, Earth, and Mars, and discover what their scars reveal. If this unfolding journey gives shape to the worlds around us, like and subscribe to the Quiet Universe channel. In the darkness before dawn, Mercury rises like a shard of cooled iron. It reflects sunlight with a harsh brilliance that hides the violence carved into its skin. At first glance, it is only a small gray sphere, but the closer you draw to it, the more it feels like the exposed core of a broken world. Everything here suggests something essential was stripped away long ago. Stone, air, and water were taken or lost, leaving metal and silence behind. The first clue appears before you even reach the surface. Mercury has no thick atmosphere to soften the transition from space. Light spills directly onto the rock. Shadows fall without blur. The horizon is sharp, almost too sharp, as if it has been drawn with a blade. That clarity sets the tone for the entire world. Nothing here is softened. Nothing is hidden by haze. Mercury carries its history openly. Standing on the surface, the sun towers in the sky, far larger than you would ever see from Earth. Its light falls in sheets so intense that the ground seems to vibrate with heat. Yet this heat slips away instantly when night arrives, with no air to hold warmth. Temperatures collapse into deep cold. It is a world of extremes separated by silence. If distance from the sun alone dictated planetary fate, Mercury should be nothing more than a cinder. Instead, it swings between furnace and ice with every rotation. Rotation itself reveals the next contradiction. Mercury is locked in a rhythm that feels unnatural. It turns 3 times for every 2 laps around the sun. Because of this strange beat, sunrise creeps across the horizon slowly, then stalls, then reverses direction for a time. The sky performs a quiet dance that defies intuition. One day here lasts 2 Mercurian years. Time stretches into something that feels unstable, as if the planet is trying to decide whether it should spin at all. Look down and you will see an ancient battlefield of craters. Some are shallow bowls, others are basins so deep that their rims rise like mountains around a sea of shadow. The largest is a scar wider than some continents. When you look closely at its shape, you can see faint rings where shock waves once rippled outward through the crust. Impacts here did not merely strike the surface, they sculpted it. Between the craters lie smooth plains that do not quite match the violence around them. These plains formed when lava once rose from fractures within the crust and spread across the landscape. The lava cooled into a hard, level surface that covers old terrain like a sheet of metal poured over broken stone. That transition from jagged to smooth reveals a deeper truth. Mercury was not always still. Something inside it once stirred, heated, and erupted. Move farther across the plains, and you will find long ridges stretching for hundreds of kilometers. These ridges form when the crust contracts. Mercury has been cooling steadily since its birth. As it cools, its outer layers wrinkle. Each ridge is a frozen fold, a sign that the planet is shrinking. It has likely contracted by many kilometers in diameter. Few planets show so much evidence of global compression. Those ridges tell us this world is still changing in the slow language of rock. But the most revealing clue lies hidden beneath the surface. Mercury has a core that dominates the interior. Most planets have crust, mantle, and core in proportions that feel balanced. Mercury breaks that pattern. Its metallic core fills most of its volume. It is a world built from the inside out. Scientists propose that a catastrophic collision in its early history may have stripped away much of its outer layers. What remains is the heavy heart of a once larger world. That metal core is still partly molten, and its motion generates a weak magnetic field. This is surprising in a world so small and so old. It should have cooled too quickly for a magnetic field to survive. Yet the field is present, faint but unmistakable. It is also offset from the center by a significant margin. Something in the internal structure is asymmetric. Something has been twisting the core with each orbit. The Sun plays a role here. Mercury travels on an orbit that varies greatly in distance from the Sun. As it swings closer, gravitational forces squeeze it slightly. When it moves farther away, the pressure eases. This tidal pressure may keep parts of the core warm enough to continue circulating. The effect is subtle and slow, Yet over billions of years, subtle forces become decisive ones. The absence of atmosphere reveals another part of the story. Molecules cannot remain bound for long. Solar radiation knocks them free. Charged particles sweep across the surface and carry the released atoms with them. Mercury has only an exosphere, so thin that particles rarely collide. When sunlight or solar wind strikes, atoms are lifted and swept away into a glowing tail that streams behind the planet like a faint plume. It resembles a comet even though it is a world of stone. This tail is a constant reminder of how much Mercury has lost and how much it continues to lose. If you could pick up a handful of the surface soil, it would feel powdery and fine. Many grains have been shattered by constant impacts. Yet beneath that dust lies material rich in metals and minerals that formed in intense heat. The planet is almost a fossil from the era when the inner system was filled with fire. Mercury's composition tells us that the early sun was fiercer than it appears today. It baked the innermost regions of the forming disk and evaporated lighter materials. Only the densest components survived. Consider how this environment shapes daily life on the surface. The horizon lies close because the world is small. The sun rises enormous and blinding. The lack of air removes all softening. There is no dusk or dawn in the familiar sense. The light changes abruptly. Shadows stretch and collapse quickly. Temperatures leap from bitter cold to staggering heat. In that cycle, you can sense the struggle of a world pushed close to the sun and forced to adapt with only metal and stone. There is a moment near perihelion when something unusual happens. The orbital speed of the planet momentarily matches its rotation. For a brief time, the sun appears motionless in the sky. Then, as Mercury moves faster along its orbit, the sun seems to drift backward. This reversal defies instinct, yet it is perfectly real. Worlds that rotate and orbit in tight rhythms often produce sky movements that feel impossible. Mercury is a case study in cosmic mechanics that rarely appear with such clarity. Its surface also reveals hints of processes that may still be active. Small hollows appear in clusters where volatile materials may be sublimating directly into space. These depressions have bright halos that look fresh, suggesting they are younger than most features around them. Even here, on a world often described as dead, there may be ongoing activity in pockets where sunlight interacts with mineral-rich zones. What Mercury teaches is not only the story of itself, but the story of heat and gravity near a star. It demonstrates how thin the line is between stability and evaporation. It shows how a planet can lose its atmosphere and still keep a molten heart. It offers an explanation for why inner worlds often become barren, while outer ones may preserve more of their air. In a sense, Mercury is the extreme end of the scale. It is a world pushed to the limit, and that limit shapes every detail. As we step back, the most compelling message emerges. Mercury is what happens when a planet experiences too much energy too early. It is a reminder that planetary identity is forged in the first few million years and then refined over billions. Its metal core and shrinking crust record the memory of that early era. If we want to understand why other worlds diverge, we must start with the one that sits closest to the furnace. The next world outward shows what happens when heat is not lost, but trapped. So we turn now toward the furnace of Venus. Venus approaches like a promise. From far away, it is the brightest planet in our night sky, a pale jewel that can cast faint shadows on Earth. It looks smooth, almost gentle, wrapped in a luminous shell. Ancient observers called it the morning star and the evening star, a twin light that seemed to follow us through history. If you judged by appearance alone, you would expect a world of calm surfaces and soft air. Yet as you descend toward it, the promise fractures. Venus is not a sister world in temperament. It is a warning written in cloud and heat. The first thing you notice is the veil. A global deck of clouds hides the surface completely. No ocean blue, no mountain outline, no land color ever reaches your eyes from orbit. The clouds are thick, layered, and highly reflective, turning sunlight away like a mirror. This veil is not decorative. It is the planet's most powerful weapon and its most perfect disguise. It allows Venus to shine brilliantly while concealing the climate beneath. The world is bright because it refuses to be seen. High above the surface, the atmosphere begins almost politely. A thin haze stretches out into space. Temperatures there are cold enough to feel familiar to any terrestrial explorer. But step downward, kilometer by kilometer, and the air begins to thicken. Carbon dioxide rises in concentration, and with it the ability to trap heat. The clouds take on their dull yellow color as sulfur compounds condense into droplets. Light becomes dimmer, flatter, and more diffuse. It is the calm before the descent into violence. At the main cloud layer, winds accelerate to astonishing speeds. They race around the planet far faster than the crust rotates beneath them. The atmosphere here moves like a separate world, a high-speed skin sliding over a slow-turning core. You can feel the planet's imbalance in this split, air that behaves like a storm-driven engine while the ground below barely turns. Why does the sky run ahead of the surface? Why does an atmosphere become its own machine? Why does the planet allow this imbalance to persist for eons? Then the descent reaches a threshold where the tone shifts. Pressure climbs quickly. The air begins to feel heavy, not as a metaphor, but as a physical presence. It pushes on every surface. It fills every crevice. It resists motion. Simply put, the atmosphere stops behaving like something you swim through and starts behaving like something you are submerged within. At these levels, carbon dioxide grows so dense that it borders on a supercritical state, carrying traits of both gas and liquid. There is no easy comparison on Earth for a sky that feels almost like fluid. Heat rises with the pressure. Every kilometer downward is warmer than the last. The greenhouse effect here is extreme. Not because Venus is closer to the Sun than Earth by a modest margin, but because the air refuses to release energy once it takes it in. Sunlight reaches the upper layers, gets absorbed, re-emitted, absorbed again, and trapped in a feedback loop that never relaxes. The planet becomes a thermal fortress. What begins as warmth becomes a prison. When you imagine the surface, discard every image of a bright tropical sister. The ground temperature remains around the melting point of lead. The pressure is about 90 times that of Earth at sea level. It is like standing beneath an ocean a kilometer deep. Only this ocean breathes acid and heat. Any unprotected machine would be crushed. Any human body would be compressed into silence before heat even became the main threat. A world can be sterile not because it lacks energy, but because it has too much of it held too tightly. There is a second contradiction hidden within this furnace. Venus rotates backward compared to the other planets, and it rotates slowly. One full spin takes longer than its year. That means if you stood on the surface and watched the sun, it would crawl across the sky at a pace that feels wrong for a day. Sunrise to sunrise lasts months. The sluggish spin is not just a curiosity. It may contribute to the atmosphere's dominance. Slow rotation weakens the planet's ability to stir heat around through surface winds, leaving the atmosphere to do the work at altitude instead. It is as if the ground surrendered control of climate long ago. The lack of a strong intrinsic magnetic field deepens the story. Earth uses its magnetic shield to deflect much of the solar wind. Mercury, even with a weak field, can still push charged particles aside at times. Venus has no such global shield. Solar wind strikes directly into the upper atmosphere, inducing temporary magnetic effects in the plasma there, but providing no stable umbrella for the air beneath. Over time, the wind strips lighter molecules away, creating a long atmospheric tail. Even so, Venus keeps its massive carbon dioxide cloak. The planet demonstrates that atmospheric loss is not only about exposure, it is also about what the atmosphere is made of and how much of it there is to lose. Radar maps reveal a surface that would be beautiful in another universe. Vast plains of hardened lava cover most of the globe. Giant volcanoes rise like islands in a sea of basalt. There are fewer small craters than you would expect because smaller impactors burn up in the thick air. The crust is old and heavy. Without plate tectonics to recycle it, Heat can build until it breaks through in episodes of resurfacing. If Earth is a planet that vents heat steadily through moving plates, Venus may be a planet that seals heat until the seal fails catastrophically. Some teams propose that its surface has been renewed in a global event hundreds of millions of years ago. Evidence is suggestive, not conclusive, but it fits the theme of a world that stores energy until it must release it violently. Why does this matter beyond Venus itself? Because Venus shows a path Earth could still take. Increase a planet's ability to trap heat. Remove its capacity to vent heat in small doses, and the climate can tip into a runaway state. A greenhouse effect is not a gentle dial. It can be a cliff. Venus is the proof of that cliff, etched in temperature and pressure. When we say a world is habitable, we are describing a balance that can fail. There is also a sliver of mystery within the veil. At roughly 50 kilometers above the surface, the pressure and temperature are close to what humans experience on Earth. In that band, the air is still acidic, still hostile, but not instantly lethal in terms of heat and squeeze. It is a thin, floating corridor. Some scientists have wondered whether microbial life could perch there, riding cloud droplets as a refuge. The idea is not confirmed, and competing analyses question the evidence that sparked it, but the corridor exists either way. Venus teases us with the possibility that even in hellish worlds, there may be narrow layers where chemistry can play a different game. The clouds themselves hold puzzles. Under ultraviolet light, dark streaks absorb radiation in patterns that shift quickly. The chemical source of that absorption is uncertain. Polar vortexes swirl at both poles with strange double-eyed structures that appear to reorganize on timescales of hours. Venus behaves like a dynamic atmosphere wrapped around a slow stone core, and we are still learning how to model that dynamism. The veil of light is also a veil of incomplete knowledge. Another consequence emerges from the sheer thickness of the air. Because sunlight is largely reflected or absorbed before it hits the ground, the surface receives only a muted glow. That weak direct heating contrasts with the internal heat trapped below. The surface becomes a place where the atmosphere dictates temperature more than the sun does in the ordinary sense. The sky is the climate engine. The ground is a passenger. So Venus stands as an extreme solution to the problem of planetary energy. It is what happens when a world holds onto an atmosphere too massive to let go. And when that atmosphere is built from greenhouse gases that amplify every photon, it is a world that turned brightness into misdirection and warmth into inevitability. It warns us that being close to the sun is not enough to burn a planet, and being far enough is not enough to save one. The details of air and rotation can change everything. Venus also enriches the central paradox of our quartet. In distance, it is not far from Earth. In mass and size, it is almost a twin. Yet in outcome, it is an opposite. The question becomes unavoidable. If two planets so similar began so near each other, why did one become a furnace and the other become a cradle? The answer cannot be a single factor. It must be a web of early accidents and long feedback loops. We will need to examine the world that stayed balanced. Not because balance is simple, but because it is the rarest outcome in the inner system. Earth enters the frame quietly. After Mercury's metal starkness and Venus's blazing confinement, this world looks almost modest. A thin blue edge clings to its curvature like a breath held in the dark. White storms coil over oceans. Continents rest in muted browns and greens. Nothing about the view announces a miracle, yet the longer you look, the more unsettling the calm becomes. Earth is not merely different from its neighbors. It is different in a way that seems statistically fragile. It is the one inner planet where water stayed liquid, air stayed thick enough to breathe, and chemistry stayed stable enough to organize into living systems. The first clue is not a number, but a feeling. From orbit, Earth is soft, light scatters. Haze blurs the limb. Shadows are not knife-sharp the way they are on Mercury. This softness is atmosphere. It is not a decorative layer. It is a filter, a blanket, and a shield. It moderates temperature, turns sunlight into weather, and makes the surface breathable. Without it, Earth would be a colder, harsher stone. With it, the planet becomes a dynamic stage. But atmosphere alone does not explain why this stage supports actors. Venus has far more air, and yet it is uninhabitable at the surface. So what is different here? Why did Earth not follow Venus into runaway heat? Why did it not follow Mars into atmospheric loss? What held the balance? The distance from the Sun matters, but only as an opening condition. Earth orbits in a narrow band where sunlight is strong enough to keep water from freezing permanently, but not so strong that oceans boil away. This corridor is not wide. Move slightly inward, and water becomes vapor. Move slightly outward, and water becomes ice. We can say this band is the habitable zone, but even that phrase hides complexity. Habitability is not a switch. It is an unstable equilibrium held up by feedback and timing. A key feedback is the water cycle. When sunlight warms the oceans, water evaporates, rises, condenses, and returns as rain. This cycle transports heat across continents, carving rivers, feeding ecosystems, and moderating extremes. It is also a thermostat. If Earth warms, evaporation increases, clouds grow, and more sunlight is reflected. If Earth cools, evaporation decreases, clouds thin, and more sunlight reaches the surface. The balance is not perfect, but it is self-correcting enough to keep oceans stable for billions of years. Why should such a reliable thermostat exist on only one inner world? How close did it come to failing early on? Another clue lies in the planet's spin. Earth rotates at a pace that creates a day of 24 hours. That timescale is not guaranteed in planetary formation. It is chemistry friendly. It allows surfaces to warm and cool without going to the extremes of Mercury's year-long nights or Venus's month-long days. It also interacts with the atmosphere to create stable circulation patterns. Winds rise, cool, and fall in belts. Oceans develop currents. Climate becomes a machine that redistributes energy rather than trapping it in one hemisphere. Could a slower Earth have become a simmering Venus? Could a faster Earth have become a storm-locked world too violent for stable oceans? The tilt of Earth's axis adds another layer. The planet leans about 23 degrees relative to its orbit. That lean creates seasons. Seasons move sunlight north and south through the year, preventing any one latitude from permanently freezing or permanently boiling. They stir the biosphere. They shape evolution by forcing organisms to adapt. Seasons do not arise only from distance. They arise from geometry. Had Earth's tilt been near zero like Mercury's, the poles might have grown cold enough to lock water away. Had the tilt been far larger, climate might have swung too violently. A narrow range of tilt seems to favor stability. Is Earth's specific tilt a rare accident? Or is it a common outcome we have not yet seen beyond our system? Beneath these surface dynamics is a deeper engine. Earth's core is large and partly molten. As the planet rotates, that moving metal generates a magnetic field. The field wraps Earth in an invisible cocoon. Solar wind particles that could strip the atmosphere are deflected around it, focusing into polar auroras instead of eroding global air. Mars once had such a field and lost it. Venus never built a stable one. Mercury built a weak one but could not keep an atmosphere anyway. Earth's field does not guarantee habitability, but without it, habitability becomes difficult to maintain over deep time. The magnetic shield is a quiet guardian. How many habitable worlds lose their atmosphere before life can take hold? How many never get a shield at all? Plate tectonics add another stabilizing loop. Earth's crust floats on a mantle that moves slowly like thick fluid. Plates collide, separate, and slide past each other, building mountains, releasing gases, and recycling the surface. This recycling matters for climate. When carbon dioxide builds in the air, tectonics and weathering draw it down into rocks. When carbon dioxide falls too low, volcanism releases more. Over millions of years, the planet breathes through stone. It is a geological carbon cycle acting like a slow heartbeat. Venus, without plate tectonics, appears to store heat and gases until they overwhelm the system. Mars, with weaker internal heat, cannot drive such recycling. Earth sits between these extremes, venting and renewing enough to avoid catastrophe. Why did Earth keep tectonics active so long? Why did Venus and Mars not? There is also the Moon. Earth has a large moon relative to its size. The moon stabilizes Earth's axial tilt over long timescales, preventing chaotic swings. It drives tides that stir coastal waters and may have aided early chemistry in shallow seas. It slows Earth's rotation slightly through tidal drag, stretching days gradually over eons. Lunar presence is not required for life in principle, but it may help life in practice by smoothing extremes. If Earth had no moon, would its tilt have wandered into instability? If the moon were smaller, would tides have been too weak to matter? If the moon were larger, would tides have been too violent? Each of these factors is known in isolation. Together they form a coincidence. A narrow orbit in a narrow light band. An atmosphere of the right thickness. A rotation of the right speed. A tilt of the right angle. A magnetic field of the right strength. Tectonics that persist. A moon that stabilizes. Take anyone away, and Earth becomes another sort of planet, not necessarily dead, but in a different regime. This clustering of conditions feels less like a rule and more like a pileup of good fortune. Is it fortune? Or is it a common attractor that we underestimate because we have only one example? Why it matters is not sentimental. It is predictive. If Earth is a rare convergence of luck, then life elsewhere may be rare. If Earth is a natural outcome of certain mass and distance ranges, then life may be common. If magnetic fields are essential, we must look for them around exoplanets. If tectonics are essential, we must infer interior heat. If a stable tilt is essential, we must model moons and impacts. Every feature of Earth becomes a filter for our search beyond the sun. Every filter shapes how we interpret the silence of space. There is a second kind of coincidence hidden in time itself. Earth did not become habitable instantly. Early Earth was a molten world. The surface cooled. Oceans condensed. Impacts rained down. Atmospheric composition shifted. Life appears in the record relatively early, but not at the beginning. It arose after a lull in catastrophe, when water had settled and chemistry had enough continuity to build complexity. Timing was crucial. If impacts had continued longer, sterility might have lasted longer. If oceans had condensed later, life might have waited. The window was not infinite. It was a moment in a violent history. How often do planets get such a moment? How often do they miss it? At its core, Earth is the watchtower of the inner system. From here, the universe is observed and interpreted. From here, telescopes peer outward, radio dishes listen, and probes are launched. But a watchtower is also vulnerable. It stands because its foundation holds. If the foundation shifts, it falls. Earth's habitability is not a trophy. It is a condition we must understand as dynamic and contingent. Seeing Earth as a watchtower makes its fragility visible. A tower in a storm remains a tower only while the storm allows it. To put it another way, Earth is not the default outcome of rocky planets. It is one outcome among many, and it sits on a knife edge between them. The proof surrounds us. Venus shows what happens when heat and air reinforce each other too strongly. Mars shows what happens when a magnetic shield collapses and air is slowly stolen. Mercury shows what happens when a world is stripped to metal and left to condense. Earth stands between these fates, not because it is immune to them, but because its feedback loops once held them at bay. Why it matters again is immediate for any long view of life. If we want to know whether we are alone, we must identify which of Earth's coincidences are essential and which are optional. If we want to know our future, we must notice how close Earth can drift toward Venus or Mars as conditions change. The sun brightens slowly. The carbon cycle can be disrupted. Magnetic fields can weaken. Tectonics can slow. Oceans can retreat. The same physics that shaped Venus and Mars still operates here. Earth is not exempt from planetary destiny. It is simply in a favorable chapter of it. So Earth becomes a question wearing a familiar face. We live on it and call it home. But in the context of the inner system, it is the least expected result. It is a world that kept its air, kept its water, and kept its internal engine alive long enough for biology to take hold. That is the coincidence of life. Not a single miracle, but a chain of them. The chain may be robust, or it may be thin. We do not yet know which. To follow this mystery further, we must leave the watchtower and walk through the ruins of the world that almost held the same chain, then lost it. Mars is the planet that wears its past like a faded photograph. From orbit, its deserts look still, a rusted globe under a thin pink sky. Yet every canyon, every delta, every layered polar cap is a sentence from an older era. Compared to Mercury's stripped metal and Venus's sealed furnace, Mars feels like the sleeping giant of the inner system. It is quiet now, but it was not always quiet. Beneath the dust lies a labyrinth of clues that lead backward to a world that once ran with water. Begin with what you see first. The color. Mars is red because iron in its soil has reacted with oxygen over deep time. The planet slowly rusting in the open air of its own history. That redness is a surface symptom, not the full story. Look past it and you notice the scale. Volcanoes broader than countries, a canyon system that stretches like a wound across a hemisphere, dunes arranged in ripples that move even today. Mars is not a static stone. It is a world still being shaped, only by slower tools. One clue is time. Mars has days almost as long as Earth's, and its seasons feel strangely familiar. Its axis tilts by about 25 degrees, close to Earth's tilt. So sunlight migrates north and south through the year in a similar pattern. Why should two planets share this geometry and yet host such different climates? What does a familiar seasonal rhythm mean on a world that cannot keep thick air? And if seasons are similar, why is the outcome so alien? Follow the seasons to the poles. In winter, each pole falls into months of darkness. Temperatures plunge so low that carbon dioxide freezes out of the air into slabs of dry ice. In spring, those slabs sublimate, surging back into gas and driving fierce winds that can exceed hundreds of kilometers per hour. You can watch the caps shrink and grow like lungs. This is not the water cycle of Earth. It is a carbon dioxide breath, a system that reveals how thin Martian air truly is. How fragile must an atmosphere be if its main gas can freeze solid each year? How close is Mars to having no air at all? The thinness becomes obvious when you imagine standing on the surface without protection. The pressure is far below what a human body can tolerate. The air is mostly carbon dioxide, and so rarefied that a strong wind would still feel like a whisper. Yet this same thin air can lift dust into global storms. Walls of fine red powder can rise to the height of mountains and wrap around the entire planet. Sometimes these storms blot out the sun for weeks. How can a nearly empty sky still produce planet-wide weather? What does that tell us about scale and energy in low-pressure environments? Mars's lower gravity adds another layer of strangeness. A person who weighs 100 kilograms on Earth would weigh less than 40 on Mars. Objects fall more slowly. Jumps carry farther. Mountains can rise larger before gravity drags them down. Olympus Mons stands about 22 kilometers above the mean surface, a shield volcano so wide that you could drive across it for days. It resembles a giant dome rather than a jagged peak, formed by lava that once poured out steadily in a low-gravity world. Why did Mars build such a monument of fire? What kind of interior heat does a world need to raise a mountain that size? If volcanism is the voice of the interior, Mars once spoke loudly. The planet's crust holds countless lava plains, fissures, and ash deposits from earlier eras, but it did not speak in the same rhythm as Earth. There is no clear evidence of plate tectonics recycling the surface. Instead, the crust cooled into a single shell. Heat rose through different vents and bulges, building volcanoes over fixed hotspots. When that heat diminished, The voice quieted. The giant did not die overnight. It fell asleep slowly. Now enter the labyrinth of water clues. Across Mars, you see dry channels that branch like river networks. You see deltas that spread into fan shapes at the mouths of ancient basins. You see layered sediments that look like the slow stacking of wet seasons. Orbiters and rovers have found minerals that almost always require water to form. These are not ambiguous shadows. They are structural memories. Mars once had liquid water on its surface, enough to carve and deposit and alter chemistry. When you see a riverbed, you are seeing time that once flowed, and yet the rivers are gone. The lakes are gone. The air that could hold water vapor is gone. The main contradiction of Mars is that it shows so much evidence of habitability, then shows its absence in the same frame. When did it slip from one state to the other? Was the change abrupt or slow? Did Mars ever have an ocean large enough to cover lowlands, or only scattered seas? How many times did it warm and cool? How many windows for life opened and then shut? One likely axis of change lies in magnetism. Early Mars appears to have had a magnetic field, generated by motion in its core. We infer this from remnant magnetized crust, frozen records of an ancient dynamo. At some point, the dynamo faded. Some teams propose rapid cooling of the core. Others suggest impacts that disrupted the interior. Whatever the cause, the effect was profound. Without a magnetic shield, solar wind could strike the upper atmosphere directly, stripping light molecules away over billions of years. A planet can lose air like a slow leak, invisible in any single century but catastrophic in deep time. This theft of air is one of the most load-bearing stories in planetary evolution. Why it matters is immediate for our broader question. If magnetic fields can fail, then habitability can be temporary, even within a stable orbit. If solar wind stripping is a common process, then many Earth-like worlds may become Mars-like before life can grow complex. If internal heat is required to sustain magnetism, then a planet's mass sets a clock on its potential for life. Mars is not just a dead end, it is a case study in how habitable eras can close. Another axis is greenhouse balance. Early Mars was warmer. The sun itself was slightly dimmer then, so warmth could not come from sunlight alone. It must have come from a thicker atmosphere, rich in greenhouse gases, trapping heat enough to keep water liquid. Once the atmosphere thinned, the greenhouse weakened, and the surface crossed a freezing threshold. After that, water could exist only as ice or transient brine. Habitability did not fail because Mars drifted outward. It failed because the thermostat broke. Even today, the surface remains active in ways that are easy to miss. Dust devils march across plains, leaving dark tracks that fade in weeks. Avalanches slide down dune faces. New impact craters expose buried ice, which then sublimates and leaves telltale stains. At the poles, spiral patterns in the ice reveal winds shaping frozen layers year after year. The sleeping giant still twitches, not with rivers, but with dust, ice, and thin air. What about life? The honest answer is that we do not know. Evidence is suggestive, not conclusive. Mars once offered liquid water, chemical gradients, and energy sources. Those are ingredients we associate with life on Earth. But ingredients do not guarantee a meal. If life began there, it may have retreated underground as the surface dried and radiation increased. It may have died out entirely, or it may never have started at all. Each possibility carries weight, because each reframes how we interpret the galaxy. If Mars was habitable and still lifeless, then Earth may be rarer. If Mars once hosted life that survived in hiding, then life may be stubbornly universal. Why it matters again is practical. Mars is the most reachable test case for theories of planetary habitability. It is close enough that we can dig, drill, and map its surface in detail. Every rover track is a line in the experiment. Every mineral sample is a clue in the labyrinth. We look to Mars to learn not only what happened there, but what can happen anywhere. There is also a human-scale perspective that does not rely on speculation. When you look up from Mars at night, Earth is only a bright dot. It feels like a star. That dot contains every ocean, every city, every story you know. Mars is a reminder of how fragile those stories are. A world can seem stable for a time, and then tip into another regime. The distance between cradle and ruin is not measured only in kilometers. It is measured in feedback loops that hold until they do not. So Mars stands as a bridge between possibility and loss. It shares Earth's day length and seasonal tilt, yet lacks Earth's thick air and magnetic shelter. It once had rivers and perhaps seas, yet now holds only ice and dried channels. It teaches us that habitability can be a phase, not a permanent label. It teaches us that the inner system is a set of timelines, not a set of static portraits. To follow the thread deeper, we must now move beneath the surfaces of all four worlds and compare the engines that shape them from the inside out. If you could peel the inner planets open like fruit, the real story would not be on their surfaces. It would be in the dark chambers beneath, where metal circulates or stalls, where rock convex or freezes, where pressure rises until it changes the very rules of chemistry. Each inner planet wears a different face, but all four faces were sculpted by engines you cannot see. Their cores are the hidden authors, writing slowly in magnetic lines, volcanic floods, and the long arithmetic of heat loss. Think of this chapter as opening a shadow library. The shelves are not made of wood but of layers, crust, mantle, core. The books are not paper but physics. Each world carries a volume about how energy moves through matter, and why some worlds keep their air while others lose it. We are not guessing at poetry here. We are following signals, measurable traces that point inward. The surfaces are the footnotes, the cores are the text. Start with Mercury. It is the smallest of the four, which should make it the fastest to cool. Small bodies bleed heat quickly. They solidify. Their internal motion quiets. So why does Mercury still generate a magnetic field at all? How can a world so old and compact keep a molten heart? One signal is its core size. Mercury's core takes up most of the planet's radius, far larger proportionally than Earth's. A large core holds heat longer, like a thick ember that refuses to go out. Another signal is the tidal flexing the Sun imposes on Mercury's orbit. When the planet swings nearer, it is squeezed. When it swings farther, it relaxes. That kneading, tiny in any moment, can add up to sustained warmth deep below. The field Mercury produces is weak, but it is real, and it proves that internal motion persists where we did not expect it. Venus poses the opposite puzzle. It is similar in size to Earth, and it likely formed with similar ingredients. Yet it has no stable global magnetic field today. Why did its dynamo fade or never form in a lasting way? Some teams propose that Venus's slow backward rotation makes core circulation less able to organize into a coherent field. Others suggest the mantle may be so dry and stiff that it cannot cool the core efficiently, leaving the core too hot and stratified to convect properly. A core does not create magnetism just by being molten. It must move in the right pattern. Venus seems to have missed that pattern. The consequence is not limited to magnetism. Without a magnetic umbrella, the upper atmosphere is exposed directly to solar wind, changing the chemical evolution of the air over time. Earth sits between those extremes. Its core is large enough and hot enough to churn, and its rotation is fast enough to organize that churning into a field. The dynamo is not a decoration, it is a live circuit. Liquid iron rises and falls, twists with rotation, and generates a magnetic shield that covers the planet. We measure this shield in compasses, in auroras, and in the way satellites must be hardened against radiation. If you ask why Earth kept its air while Mars lost so much, you are really asking about the continuity of this dynamo. Why did Earth sustain it for billions of years? Why did Mars not? Mars gives us a clue by its absence. It once had a magnetic field. We know this because ancient crust in the southern highlands holds remnant magnetization, like frozen fingerprints of a field that no longer exists. At some point, the core cooled enough to stop vigorous convection, or an impact disrupted the internal layering. The field weakened and then died. After that, solar wind began stripping the upper atmosphere steadily, not in a dramatic collapse, but in a slow theft across deep time. The field's disappearance turned a potentially stable climate into a leaking vessel. How many planets across the galaxy follow this same trajectory, warm and wet in youth, then exposed and dry in age? Magnetism, though, is only one axis. Heat itself is another, and heat depends on pressure and composition. In the early solar system, all 4 inner planets started hotter than they are now. Their surfaces were oceans of magma. As they cooled, each planet followed a different thermal path. Mercury's small mantle froze early, but its oversized core stayed partly molten. Venus's mantle may have become a thick lid, trapping internal heat and preventing plate tectonics. Earth's mantle remained mobile enough to drive plates, allowing continuous venting of heat. Mars, smaller and farther out, lost internal heat quickly and fell into dormancy. 4 cooling curves, 4 outcomes. Pressure in the interior shapes how those curves play out. Under higher pressure, rock behaves differently. It may become more viscous, less willing to convect. It may change mineral phase, altering how heat moves. Earth's interior pressure supports a layered mantle that can convect in long-lasting patterns. That convection is what drives tectonics, which then cools the core, which sustains magnetism. Venus, with similar pressure but likely less water in the mantle, may have higher viscosity, slowing convection. If convection slows, the core cools differently, and the dynamo fades. Does the presence of water in mantle minerals become a silent lever that decides dynamo fate? Does a wet mantle help a planet breathe heat out gently instead of bursting? In everyday language, imagine stirring a pot of thick honey versus a pot of thin soup. Both hold heat, but only one circulates easily. Mantle viscosity is the honey. Water is the thinning agent. Earth has enough internal water to keep the mantle moving. Venus may not. Mercury and Mars cooled too quickly for viscosity differences to matter as much. This is a simple analogy for a deep process. It tells you why similar planets can diverge sharply with a single hidden ingredient. Composition also matters. A core rich in light elements, sulfur or oxygen or silicon, lowers the melting point and keeps liquid metal available longer. Mercury's core may contain such elements, extending its dynamo life. Mars's core may once have had enough sulfur to stay molten for a time, but not enough to maintain convection once the mantle cooled and insulated it. Earth's core composition supports long-lived convection in tandem with mantle cooling. Venus's core composition is less certain, but if it is stratified by light elements, convection could be choked. The signal here is indirect, inferred from gravity fields, rotational behavior, and surface geology. Yet the pattern fits the outcomes we see. These internal differences explain surface features that otherwise look unrelated. Mercury's global ridges come from contraction, a crust wrinkling as the interior cools. Venus's widespread lava plains suggest episodic resurfacing, a lid that traps heat then breaks violently. Earth's mountain ranges and ocean basins are the scars of plate motion, a sign of a mantle that never fully froze. Mars's giant volcanoes and long quiet plains reflect a world that once had hot spots but could not recycle crust. When you compare surfaces, you are reading the thermodynamics of the core. Why does this matter for the larger narrative of habitability? First, habitability depends on air, and air depends on magnetism and volcanism. A planet that loses its field may lose its atmosphere. A planet that vents too much gas may trap too much heat. Second, habitability depends on stable temperature ranges, and those ranges depend on how interior heat is released over time. Third, habitability depends on chemical cycling, and chemical cycling depends on tectonics and volcanism, which depend on mantle convection. These are not individual knobs. They are a coupled system, a machine whose state is set by the core. Here is the contradiction that keeps returning. Earth and Venus began with similar sizes and sunlight, yet their cores and mantles evolved into opposite regimes. Earth ventilated its heat through moving plates. Venus appears to have sealed its heat behind a rigid crust. Earth sustained a field. Venus did not. Earth stabilized oceans. Venus accelerated into runaway heat. Is the difference truly a matter of initial water, or was there a pivotal impact that retuned one interior but not the other? Was there a moment early on when Venus could have become a watchtower too, then slipped into the furnace path? Mercury and Mars add a different lesson. Size sets a clock. The smaller the planet, the faster its interior cools. Yet Mercury defies the clock slightly because of its massive core and tidal heating. Mars follows the clock, losing dynamo activity and internal volcanism sooner. So size is a rule with exceptions, and the exceptions matter. They tell us that habitability cannot be inferred from mass alone. You must look for the silent signals of interior behavior. There are signals we can measure beyond our system. For exoplanets, we look for density, orbital resonances, stellar wind conditions, and possible magnetic interactions. We search for atmospheric retention over time. If a planet is close to its star, but still holds thick air, perhaps it has a long-lived dynamo or a massive core. If a planet is in a habitable light band but show no air, perhaps its field died early. Mercury, Venus, Earth, and Mars become templates for this inference. Their divergent cores are a key to reading distant worlds. Notice how these interior stories also shape time. A planet can pass through habitable phases. Mars likely had one. Earth has one now. Venus may have had a shallow one before runaway trapping. Mercury never had one at the surface. The length of such phases depends on internal cooling and dynamo longevity. If the core stays active, habitability can endure. If the core quiets, habitability may end even if light conditions remain favorable. This is a deep time perspective. It shifts the question from where habitability exists to when. We should also hedge where uncertainty remains. Venus's core state is not directly measured. We infer it through models and indirect data. Competing views disagree about whether Venus ever had plate tectonics similar to Earth, or whether it always operated under a stagnant lid. The evidence is consistent with both in different ways. Mercury's core composition is inferred but not fully resolved. Mars's dynamo shutdown timing is bracketed, not exact. These uncertainties do not weaken the argument. They tell us where the shadow library still has missing pages. What remains solid is the coupling. Magnetic fields, heat flow, pressure-driven mineral behavior, and volatile cycling are tied together. Each inner planet represents a different equilibrium within that coupled set. Mercury is a metal-heavy world with a surviving ember of magnetism. Venus is a heat-trapped world with a sky that dominates its fate. Earth is a ventilated world with a living dynamo and active cycling. Mars is a cooling world whose field died and whose air slowly escaped. 4 divergent cores, 4 divergent futures. We began this story with a broken mirror of destinies. Now you can see the invisible hand behind the fracture. It was not distance alone, not size alone, not a single catastrophe. It was the slow, persistent behavior of planetary interiors. The cores wrote the script, and the surfaces performed it. The next clue lies in the violence that struck these interiors from above, the ancient bombardment that reshaped their trajectories. Before the inner planets became the worlds we recognize, they lived through an era that barely fits into human imagination. The young sun had not yet settled into calm adulthood. The solar system was a crowded construction site, filled with leftover debris, wandering protoplanets, and swarms of rock and ice still searching for stable orbits. In that chaos, impacts were not occasional accidents. They were a routine language. Every collision was a sentence, every crater a paragraph, and every basin a chapter that rewrote what a planet could be. The first clue is written across all 4 surfaces. You cannot stand on Mercury, Venus, Earth, or Mars without seeing the scars. Craters overlap craters. Basins dwarf everything built later. Their density is not random. It is a fossil record of a time when the inner system was hammered repeatedly by bodies ranging from boulders to worlds. The bombardment was not a single day of fire. It was a long season of violence, fading slowly as debris was cleared or thrown away. Why should early impacts matter so much for destiny? Because a planet at birth is soft, its crust is thin, its mantle is hot, its atmosphere is fragile. If it has one at all, a large impact does not merely mark the surface. It injects energy that can melt rock, reform crust, alter rotation, and strip air. It can heat the core or fracture it. It can deliver volatiles that later become oceans, or remove volatiles by blasting them into space. When a planet is young, a single collision can push it from one evolutionary path to another. Consider Mercury again in this light. Its core is disproportionately large. That fact has led to a long-standing hypothesis. Mercury may be the remnant of a bigger planet that suffered a colossal collision. In that scenario, a massive impact stripped away much of its mantle and crust, leaving an iron-rich survivor. Evidence for this is indirect, but the outcome aligns with what we see: a dense world with too much metal for its size. If this happened, Mercury was not born a metal world. It was made into one by violence at the right moment. A different impact history could have left Mercury as a more ordinary rocky planet, perhaps with a thicker mantle and a different thermal fate. Venus holds a different kind of scar. Its surface shows relatively few small craters when compared to Mercury and Mars. That does not mean it avoided impacts. It means its surface has been reset. Large sections of Venus appear to have been resurfaced by lava in a geologically recent era. One possible trigger is interior heat trapped beneath a thick lid, but impacts could have contributed by fracturing the crust or altering heat flow. In a planet already sealed by greenhouse air, a surge of volcanism would release more gases, thickening the atmosphere and pushing the climate further into runaway trapping. The bombardment might not be the main driver of Venus's furnace, but it may have been an early accelerant. Earth presents the most delicate case. When you search for its oldest craters, you find few. Plate tectonics and erosion erase them. Yet the absence of scars is itself a clue. Early Earth was hit heavily. We infer this from lunar crater density and from isotopic traces in ancient rocks. Those impacts likely delivered water and other volatiles. They also may have driven repeated melting and crust recycling, which could delay or reset early life. There is a thin line between a bombardment that seeds oceans and one that sterilizes them. Earth seems to have been struck with enough force to build its inventory of water and carbon, but not with enough persistence to prevent life from gaining a foothold. That is another coincidence in the chain. Mars shows the record more clearly than Earth. The southern highlands are heavily cratered, ancient, and dense with scars. The northern lowlands are smoother and younger. The contrast suggests that Mars experienced a major reshaping event. Some propose a giant impact carved out the northern basin, creating a lowland that could later host an ocean. Others see the lowlands as a product of internal processes. The debate continues. But the possibility is important. A single enormous collision can rearrange a planet's hemispheres, tilt its axis, and change its geology for billions of years after. Mars may have lost or gained a potential ocean because of one catastrophic strike. If impacts shape surfaces, they also shape rotation. Planets spin the way they do, partly because accretion and impacts added angular momentum unevenly. Mercury's peculiar resonance could have been nudged by impacts that mattered before tidal locking took hold. Venus's slow, backward spin may be the most dramatic example. A collision large enough and angled correctly could reverse rotation, or set a planet into a state where thermal tides later grind it down into a retrograde crawl. This is not certainty. Multiple models exist, but the principle is solid. Rotation is not purely set at birth. It is sculpted by blows that arrive after birth. Impacts also decide atmosphere fate. When a large body strikes, it releases energy equal to millions of nuclear bombs. That energy heats the air. It can blow a significant fraction into space. On small planets like Mars, repeated impacts could thin early air directly, making the planet more vulnerable to later solar wind stripping. On Earth, impacts might have removed air at times, then delivered new gases through the composition of the impactors. The net effect depends on size, speed, and timing. The bombardment is not a simple gain or loss. It is a turbulent exchange between planet and skies. The clue continues in chemistry. Many volatiles in the inner system, including water, carbon compounds, and certain noble gases, likely arrived via impacts from farther out. The early disk near the Sun was too hot for easy preservation of many ices. Bodies from cooler regions could carry them inward. If so, then the oceans of Earth and any early seas of Mars were partly gifts from collisions. The dryness of Mercury and Venus could come partly from their proximity to the Sun, but also from an impact history that failed to deliver enough volatiles or that removed them through high-energy stripping. We often ask why Earth has oceans. The unromantic answer may be that it was hit at the right times by the right kind of debris. There is a broader context to this violence. The young system likely experienced a chaotic rearrangement of giant planet orbits. As those massive bodies shifted, they could destabilize belts of asteroids and comets, scattering them inward. This would spike impact rates in the inner system, an episode sometimes called a late heavy bombardment. Evidence for its timing and intensity is debated, but the crater records on Moon and Mercury support a period of enhanced impacts early on, whether it was a sharp spike or a long tail. The result was a reshaping of inner worlds at a sensitive stage. Why does this matter for destiny rather than just geology? Because impacts are decision points. In the language of evolution, they are selection events. They remove possibilities and lock others in place. A planet that loses its atmosphere early may never recover it. A planet that gains water early may enter a stable cycle that protects habitability. A planet whose spin is altered may shift climate patterns for billions of years. A planet whose crust is fractured may unleash volcanism that changes its sky. Destiny in the inner system is the sum of slow processes plus a few violent inflection points. This also explains why no single factor tells the whole story. Mercury's metal heart is an interior story and an impact story. Venus's runaway greenhouse is an atmospheric story and a resurfacing story, possibly shaped by impacts. Earth's habitability is a thermal story, a tectonic story, and a delivery story by collisions from beyond. Mars's ruin is a magnetic story, an atmospheric stripping story, and perhaps a hemispheric impact story. The bombardment weaves through all of them. Some uncertainties remain, and we should respect them. The exact scale of the late heavy bombardment is still contested. The Mercury stripping hypothesis competes with models of chemical sorting in the early disk. The northern lowlands of Mars can be explained without a single giant impact. Venus's retrograde spin may require more than one mechanism. These are active research fronts. Yet even with uncertainty, the core insight stands. Impacts are not cosmetic, they are architects. We can also see the human-scale echo of this era in the landscapes astronauts and rovers explore. Every crater rim is a frozen shockwave. Every brecciated rock is a memory of compression. When we read these surfaces, we are reading an old battlefield that never truly ended. It only quieted. And the quiet allowed the slow interior processes of Chapter 5 to resume shaping each world without interruption. So the bombardment era is the firestorm that separated branching paths, while the cores were the engines that carried those paths forward. Together they explain why 4 planets born from one disk now look like 4 different categories of reality. The broken mirror was shattered by impacts, and then each fragment cooled into its own form. But even after the rocks stopped falling so often, a subtler theft continued. The gradual stripping of air and water by light, wind, and time. After cores and impacts, there is a third axis that decides planetary fate, the thin and restless layer we call air. Atmospheres are not decorations. They are the negotiators between sunlight and surface, the membranes through which a planet breathes heat, holds water, and lets chemistry run long enough for complexity to grow. In the inner solar system, the four worlds did not merely inherit atmospheres, they fought for them. Some kept what they had, some lost almost everything. One hoarded too much. The result is not just weather, it is destiny. Volatiles are the raw material of atmospheres. Water, carbon dioxide, nitrogen, sulfur compounds, noble gases, and a zoo of trace molecules. They are called volatiles. Not because they are trivial, but because they evaporate, condense, and migrate easily compared to rock and metal. In the early solar system, volatiles arrived by multiple routes. Some were baked into the forming planets, some were delivered later by impacts from colder regions, some were released from interiors by volcanism. Each planet began with a different inventory, then faced different levels of theft. The first theft is simple heat. Close to a star, molecules in the upper atmosphere move faster. When enough of them exceed escape velocity, they drift into space and never return. This thermal escape is a quiet leak, accelerated by high temperature and low gravity. Mercury, sitting closest to the Sun, never had a chance to keep a thick atmosphere for long. Its gravity is weak, its surface is hot, and its upper layers are constantly stirred by solar radiation. Whatever air Mercury may have had early on may have boiled away quickly, leaving only a thin exosphere replenished by surface sputtering. Mercury is the extreme example of a world whose air was stolen almost as soon as it formed. The second theft is light itself. Ultraviolet photons break molecules apart. Hydrogen, once freed from water vapor or other compounds, is especially easy to lose. Venus provides a dramatic case. Today, Venus is dry. Despite being Earth's near twin in size, one explanation is that early Venus may have had significant water, perhaps even shallow seas. As the planet warmed, more water evaporated into the atmosphere. Ultraviolet light split those molecules. Hydrogen escaped to space. Oxygen either reacted with the crust or was dragged away by solar wind. Over time, the planet bled out its water, leaving a dense carbon dioxide sky. Evidence from the ratio of deuterium to hydrogen in Venus's atmosphere suggests a long history of water loss. Though the scale and timing remain under study, the important point is that the theft of hydrogen is irreversible. Once the lightest element leaves, oceans cannot return easily. The third theft is the solar wind, an unceasing stream of charged particles flowing outward from the sun. Where a planet has a strong magnetic field, the wind is deflected. Where it does not, the wind can interact directly with the upper atmosphere, knocking particles free and carrying them away. Mars is the classic victim. After its dynamo faded, the solar wind began stripping its air steadily, not in a single apocalypse, but in a slow attrition. We measure this process even today. In the upper atmosphere, ions are picked up by the wind and swept into space. Over billions of years, this theft thinned the sky enough to collapse the greenhouse effect, freeze the surface, and dry rivers into fossils. Mars teaches that a planet can lose habitability without moving an inch, simply by losing its shield. Earth sits on the other side of this contrast. Its magnetic field protects much of its atmosphere from direct solar wind erosion. That does not mean Earth is immune to loss. The upper atmosphere still loses hydrogen and helium, but the rate is slow enough that oceans persist. Earth also has a cold trap, a region in the atmosphere where water vapor condenses before reaching the high altitudes most vulnerable to ultraviolet splitting. This trap is a quiet guardian. It keeps water low, preventing rapid hydrogen loss. Venus lacks such an effective trap because its atmosphere is hotter and more saturated. In a subtle way, this difference in vertical temperature structure becomes a difference between an ocean world and a dry furnace. Volcanism is the other side of the ledger. A planet can lose air, but it can also replenish it from within. Mercury's interior is too quiet now to do much of this. Mars vented gases early, but as its interior cooled, its volcanic breathing weakened, leaving no strong replacement for the air that escaped. Venus, by contrast, may still vent gases episodically, thickening an already massive atmosphere. Earth vented continuously through plate tectonics, and those vents fed a stable cycle rather than a runaway. Air is not only lost, it is negotiated between sky and stone. The negotiation depends on chemical feedback. On Earth, carbon dioxide dissolves into rain, reacts with rocks, and is locked into carbonates. Subduction drags those carbonates downward, and volcanism releases carbon dioxide back. This slow cycle keeps the greenhouse effect within a moderate band. Mars has evidence of some rock weathering, but without active plate tectonics, its carbon cycle could not regulate itself in the same robust way. Venus, without ocean water at the surface and with a stagnant lid crust, lacks the same efficient drawdown. Carbon dioxide accumulates there until it dominates climate. This is why too much air can be as fatal as too little. The theft of air is one tragedy. The hoarding of air is another. Pressure changes everything about surface physics. On Venus, the pressure is so high that carbon dioxide becomes a supercritical fluid near the ground, neither gas nor liquid in the familiar sense. Heat transfer becomes efficient, and convection in the lower atmosphere behaves differently. Weathering chemistry accelerates under such pressure, but without liquid water to carry products away, the balance is not stabilizing. On Mars, pressure is so low that liquid water is unstable at the surface for long. Ice jumps directly to vapor, evaporating into a sky too thin to hold it. On Mercury, pressure is almost non-existent. Minerals exposed to sunlight release atoms directly into space. These pressure regimes are not secondary details. They are the stage on which every other process unfolds. There is also the role of impacts in volatile history. If Earth and Mars received significant water and carbon from later impacts, then their volatile inventories were not fixed at birth. A burst of deliveries could refresh an atmosphere, while a burst of high-energy impacts could strip one away. The early era was a turbulent accounting system. Even after impacts waned, occasional strikes still brought gases to Earth, and probably to Mars in smaller doses. Mercury's proximity and thin air kept such deliveries from accumulating. Venus may have gained volatiles early, but lost water later through light-driven theft. The volatile story is not a single direction. It is a multi-step path with switches that lock. Why it matters extends beyond our quartet. Volatiles are the currency of habitability. Without water, life as we know it struggles to begin. Without a stable greenhouse balance, temperatures swing into sterility. Without air thick enough for pressure stability, liquid phases vanish. The theft of air is the theft of potential. When we search exoplanets, we are not only searching for the right distance from their stars. We are searching for a stable volatile budget over time. That means inferring magnetism, interior heat, delivery history, and stellar wind strength. Habitability is a history problem, not only a location problem. In plain terms, atmospheres are the long memory of a planet. They record not just present conditions, but billions of years of negotiation and loss. Mercury's near vacuum says its memory was erased early. Venus's crushing sky says its memory grew too heavy to bear. Earth's balanced air says memory found a dynamic equilibrium. Mars's thin sky says memory faded under relentless wind. 4 atmospheres, 4 biographies. We should note uncertainties with care. The early water content of Venus remains debated. The exact timing of Mars's major atmospheric losses is bracketed by multiple measurements. Not pinned to a single date, the volatile delivery rates during the bombardment era are inferred statistically rather than observed directly. Yet the direction of the story is consistent across models. Volatile fate is sensitive to mass, sunlight, and magnetic shielding, and those sensitivities produce the outcomes we see. So the theft of air is not a side chapter. It is the hinge that turns interiors and impacts into climate. It decides whether a core's heat creates a hospitable ocean or a locked furnace. It decides whether an impact's delivery of water becomes a sea or a brief wet trace erased by evaporation. Air, or the absence of it, is the medium through which planetary destiny becomes visible. Now that we have traced how cores diverged, how impacts shattered paths, and how atmospheres were lost or trapped, we are ready to face the last question of Act 2. What futures await these four worlds as the sun itself slowly changes? We have walked through metal, furnace, cradle, and ruin. Now we stand far enough away to watch all four worlds at once, not as separate stories, but as a single system moving through deep time. The inner planets are not finished products. They are long processes that continue to unfold under a sun that itself is changing. The same star that split their fates is still writing the next pages. Slowly, steadily, almost without drama, yet with consequences that are absolute. Start with the simplest truth. The sun brightens as it ages. This is not a sudden flare, but a gradual increase in luminosity over billions of years. A star like ours turns hydrogen into helium in its core. As helium accumulates, the core contracts, the surrounding shell heats, and the star emits more energy. What seems fixed in a human lifetime drifts in stellar time. How does a quiet brightening rewrite the habitable corridor? How long can any inner world stay in balance when the lamp above it creeps brighter each epoch? Mercury remains closest to the furnace, and its future is the most direct. As the sun brightens, Mercury will absorb more heat, but the planet has almost no air to trap or redistribute it. Its day side will grow hotter. Its night side will still plunge cold, and its crust will continue to contract. It will not become a Venus or an Earth. It will become more itself, more extreme, more brittle. A metal world pushed further toward its thermal edge. Over immense time, Mercury may lose more of its surface volatiles, atom by atom, tail by tail. What does it mean for a world to age by shedding its last traces into space? Can a planet that has already been stripped be stripped even further, until only a core speaks in silence? Venus is already in a runaway state. A brighter sun does not change its category, but it does deepen its lock. The upper atmosphere will warm. The rate of hydrogen escape from any remaining trace water will remain high. The thick carbon dioxide cloak will stay dominant. Venus is a world where the climate cliff has already been crossed. The future there is not a transformation into habitability. It is a slow reinforcement of uninhabitability. If Venus once brushed the edge of a mild era, that edge is long gone. How much brighter must the sun become before even the temperate cloud layer shrinks away? What does it mean for a world to be trapped not by distance, but by its own sky? Earth stands in the narrowest corridor of all, and its future carries the most weight for us. As the sun brightens, the habitable band shifts outward. Earth will slowly move toward the inner edge of stability, not because its orbit changes dramatically, but because the energy budget does. More sunlight means more evaporation. More evaporation means more water vapor, which is itself a greenhouse gas. At some point, the water cycle that stabilizes climate can flip into a feedback that amplifies warming. A planet does not need to look like Venus to begin walking toward Venus. When will Earth's oceans begin to boil in the long view? Is the march slow enough for geology to compensate? Or does stellar brightening outpace even tectonic breathing? Some models suggest that within a billion years, Earth could enter a moist greenhouse phase. In that regime, water vapor penetrates higher into the atmosphere, ultraviolet light splits it more efficiently, and hydrogen escape accelerates. Oceans do not vanish overnight. They leak away over tens or hundreds of millions of years. The end state is a drier world with less capacity to regulate temperature. This is not certain in timing, and competing models offer different thresholds. But the direction is physically grounded. Why it matters is plain. Earth's habitability is not permanent by default. It is a chapter with a closing page. The watchtower does not stand forever. It stands while the sun allows it. Mars, paradoxically, may experience a brief softening before the sun's long fade overtakes it. As solar output increases, higher latitudes could warm. Subsurface ice could melt in places. Liquid water might transiently appear in brines or shallow pockets. The atmosphere, however, is too thin to hold stable seas for long, and the planet lacks an active dynamo to rebuild a thick sky. Any warming is likely to be temporary and incomplete, a mild thaw on a world whose main trajectory is still cold. Could Mars gain a second habitability window? If it does, would it be long enough to matter for biology, or only long enough to matter for our understanding of planetary timing? The futures of these worlds are also tied to their interiors. Mercury's core will cool further, but tidal flexing may keep part of it molten longer than a naive clock predicts. Venus may continue to trap interior heat and release it in episodic resurfacing. Earth's tectonics will gradually slow as interior heat declines, changing the carbon cycle over vast time. Mars will keep cooling, its volcanic voice fading further into stillness. These internal trajectories do not stop when atmospheres stabilize. They continue to shape surfaces and skies long after the main divergence is set. If habitability is a history problem, then futures are part of that same history. There is another, farther horizon. When the sun exhausts hydrogen in its core, it will expand into a red giant. Its radius will swell outward, and its brightness will surge far beyond today's gentle drift. Inner orbits will be engulfed or scorched. Mercury's fate is almost certainly absorption. Venus's fate is likely the same. Earth's fate is uncertain in detail, but its surface will not survive in any familiar form. Mars may be heated intensely, perhaps pushed into a brief temperate regime before the outer expansion and mass loss reshape orbits. This red giant era is not a rumor. It is standard stellar evolution. It is the long fade of the inner system written into physics. Why does a system that can host life for billions of years still move toward a future where its cradle is erased? What does that teach us about life as a temporary arrangement inside a star's biography? The biggest reveal of our investigation is this. The inner planets are not four isolated curiosities. They are four time phases of a single planetary logic. Mercury shows the stripped end of early heat. Venus shows the runaway end of atmospheric trapping. Earth shows the rare balance that can host complexity. Mars shows the loss that follows when shielding and air fail. These are not only places, they are outcomes that any rocky world can pass through, depending on mass, rotation, volatiles, and the clock of its star. Our solar system did not produce one habitability story. It produced a full menu of possible endings and one delicate, temporary middle. Map that insight outward to the galaxy and the implication expands. Many planets may begin like Earth and drift toward Mars. Many may begin mild and tip into Venus. Many may be stripped like Mercury before they can try another path. Some may hover in balance for a long time, long enough for life to rise. Look up and ask what kind of world it lives on. Why it matters is unsettling and clarifying. Habitability is not a location pinned in space. It is a corridor pinned in time. When we search for life, we must search for worlds that are not only in the right place, but in the right era. Sharpen that further. A planet can be habitable for 1 billion years and still be sterile if life never begins. Another can be habitable for only 100 million years and still spark biology if conditions align quickly. The inner system tells us that duration and timing are as crucial as distance. It also tells us that a star is not just a backdrop. The sun is the metronome of all four futures. As it speeds up or slows down in brightness, it drags the habitable band with it. Every rocky world near every star is riding the same kind of moving wave. Why it matters for us is not abstract. It frames our own moment. We are living during Earth's favorable chapter, not at the beginning of it and not at the end. The coincidence of life is coincidental in time as well as in structure. There will be a last coastline, a last forest, a last stable ocean current, far in the future, but real. That does not cheapen the present. It makes the present more precise. It makes the watchtower we stand on feel both miraculous and finite. The four futures also suggest a different kind of humility. We often ask which planet is most like Earth. But the deeper question is which phase of planetary evolution is most like Earth right now? A world that is hotter than Earth today could be Earth's future. A world that is colder than Earth today could be Earth's past. Mercury, Venus, Earth, and Mars become a single timeline spread across 4 orbits. The broken mirror is also a clock. So as the inner system fades, it does not fade into sameness. It fades into continued divergence, continued extremes, and continued motion toward the red giant horizon. The sun's light rising slowly is not a footnote. It is the last great sculptor of inner worlds. Under that light, Mercury sharpens into metal silence. Venus deepens its furnace. Earth walks toward a drier era, and Mars tastes brief warmth before returning to cold. The quartet remains a quartet to the end. Explore deeper cosmic stories with us. Like and subscribe to the Quiet Universe channel. And as we turn from futures to meaning, we must ask what these 4 destinies say about life's place in a universe that never stops changing. The 4 inner worlds now drift in your mind as more than planets. They have become 4 mirrors, 4 warnings, 4 lessons in how matter and light contend with time. From a distance, they look like beads on a string, neat, aligned, orderly. But step closer and you see the fractures beneath the calm. Mercury burned and stripped, Venus drowned in its own warmth, Earth balanced on narrow terms, Mars cooled, dried, and fell silent. Each world is a single answer to a question the sun asked billions of years ago. And now, with their stories told, only one frontier remains, the frontier of meaning. Picture the inner system from far beyond the orbit of Mars. The sun is a pale ember. The 4 worlds move in slow arcs, each tracing out a destiny we have now followed from furnace to freeze. There is no sound in this view, only motion. This is the solar system without interpretation, a clock made of gravity. Yet interpretation is what we bring to it, without us. These orbits are only geometry. With us, they are creation, loss, balance, warning. They become a way to think about impermanence. Earth stands out as the sphere that made observers. That alone reframes the entire system. Life turned one world into a witness. And through that witness, the universe begins to look back at itself. But life is not an automatic outcome of physics. It is a narrow response to precise conditions. The coincidence of life is as much about timing as chemistry, as much about a planet surviving long enough to foster complexity as about the formulas that drive carbon chains. You can walk through all 4 worlds and see places where life could not begin, or could not last, or could not adapt fast enough. You understand that Earth's stability is not a privilege guaranteed by its orbit. It is a moment. From that moment arises a different vision of time. Humans measure time in days, years, generations. Planets measure time in the cooling of cores, the slow retreat of atmospheres, the wandering of orbits. Stars measure time in hydrogen spent and helium gained. These scales overlap but do not align. Earth's entire human story fits inside a sliver of Earth's long temperate era. When you speak about the future of worlds, you must admit that the universe's clock does not keep human hours. What feels permanent to civilization is a blink in the biography of a star. Yet the inner planets also offer a quiet generosity. They show that change is not sudden in cosmic terms. They show that destiny is written with slow motion, not sleight of hand. A planet does not collapse in a century. A core does not freeze in a millennium. An atmosphere does not vanish in one season. This slowness is what makes life possible at all. It gives landscapes time to stabilize, oceans time to circulate, biology time to experiment. Slowness is the mother of complexity. But the same slowness that nurtures also erases. The sun's brightening is patient, but it is certain. Earth's oceans will not survive forever. Mars, even if thawed by that future brightness, will not hold its air long enough to build a new biosphere. Mercury and Venus will remain locked in their extremes. Time is impartial. Every arc has an end. There is no tragedy in this, only scale. A world is a vessel for a chapter. The chapter ends. The vessel cools, and the story continues elsewhere. Think of a single line spoken near the edge of this system, not as a prophecy, but as a refrain. We read the universe by reading the scars it leaves. Every crater, ridge, cloud, and dry basin is a memory written in matter. And because Earth developed minds capable of interpreting those memories, the inner planets become more than experiments. They become archives of possibility. They whisper how worlds succeed or falter, how atmospheres rise or collapse, how oceans form or fade. They tell us that life thrives where matter hovers on the narrow line between stability and change. And so the philosophical echo emerges. When you study planets, you study the conditions that allow awareness to bloom within a small patch of chemical order. When you study planetary futures, you study the lifespan of that awareness. The four worlds form a meditation on chance, on fragility, on the fact that something as subtle as mantle water content or rotation rate can change the entire arc of a biosphere. These are not just facts. They are reminders. To see Venus is to see what too much heat can do. To see Mars is to see what too little air can do. To see Mercury is to see how proximity strips away every comfort. To see Earth is to see the improbable middle that gave rise to thought. The inner planets also challenge a quiet assumption, the idea that the universe is designed around life. Instead, they show a universe indifferent to life, yet capable of hosting it whenever narrow conditions align. They show that life is a local triumph against a cosmic backdrop that does not bend itself to nurture. That recognition does not diminish the significance of life, it sharpens it. Life becomes a statement of resilience inside a system that tends toward extremes. Consider also humility. Earth is the only inner world that looks back at itself through instruments, that maps other planets, that deciphers atmospheres light years away. But that ability does not lift Earth above the others. It binds Earth more tightly to them. Knowledge is the echo of survival. If Earth had slipped into the path of Venus or Mars, there would be no eyes to read the scars. Awareness is not a reward. It is a symptom of conditions that hold just long enough. Now return your gaze to the sun, not as a deity, but as the engine of all four stories. Its light carved every destiny we have studied. It warmed oceans, blasted atmospheres, shaped orbits, and now slowly brightens toward an age where none of these worlds will remain as they are. If we seek a cosmic lesson, it is not in the individual fates of Mercury, Venus, Earth, or Mars. It is in the recognition that stars sculpt possibility, then take it away. The universe creates windows for life and closes them without intent. What remains is the open question at the center of this echo. If four adjacent worlds can show such different paths, and if habitability is a corridor that opens and closes over time, then what does it mean for life to search beyond its birthplace? Is life an accident of Earth's moment, or a signature the cosmos writes again and again wherever the balance briefly holds?